Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 1 from the June 2019 Core Mathematics C34 paper from the International A-Level Edexcel exam. This corresponds to the P3 paper, this question of the new specification from 2020 onwards. And this is a question about iteration and numerical methods. And I'm going to address an issue which a lot of students ask about, which is how does this particular method work? What is the rationale behind it in order for us to solve equations of this type? Okay, and this is something you don't really need to know for the exam. Okay, you just need to know how to apply this method, but it's always good to have an understanding of why and how things work. So I'm going to devote a bit of time to explain that for those students who are curious about it. So first of all, we're given this equation f of x equals 2x cubed plus x minus 20. And they're asking us to rewrite the equation f of x equals 0 in the form x equals the cube root of a minus bx, where a and b are positive constants to be determined. Okay, so basically they're getting us ready in this question to find the root or roots of this equation, f of x equals 0. The roots of this equation are when it equals 0, so when f of x equals 0. That's what they're getting us ready to do. That's where this process of iteration will help us, as we'll see in a few minutes. So first of all, what they've done is they've asked us to make one of these x's the subject, and obviously the one that they've asked us to make the subject must be the one which is associated with the x cubed, because the answer is going to have to be cube rooted. So it's going to be this x that we have to make the subject, and then cube root both sides. Okay, so that's obviously what they've done. So first of all, we're going to put f of x equals 0. So we've got 2x cubed plus x minus 20 equals 0. So that's the first step. Okay, that's our first step here. And now what we're going to do is we're going to make this x cubed the subject. So what we have to do is we have to add 20 and subtract x from both sides. So you've got 2x cubed is equal to 20 minus x. And then we can divide both sides by 2. As you can see, they've put them as separate terms. So I'm going to divide each term by 2 separately. So 20 divided by 2 is 10. And x divided by 2 is x over 2, or you can say a half x. And then simply cube root both sides. So x is equal to the cube root of 10 minus a half x. Remember, we don't have to put plus or minus because this is an odd power that we use, so the odd root. There's only one solution, not two. Okay, now, so that's what we've done. So we see that a is 10 and b is a half. A is 10 and b is a half. We don't have to write that down, just put it in the form, but I'll just write it down anyway. Okay, so those are positive constants. A is 10 and b is positive a half. The minus in front of it also makes that negative now. Now, for part B, it says starting with x1 equals 2.1, use the iteration formula xn plus 1 equals the cube root of a minus b x power xn with the numerical values of a and b to calculate the value of x2 and x3, giving you answers to 3 decimal places. So basically, our iterative formula is xn plus 1 is equal to the cube root of a, which is 10, minus b, which is a half, xn. And what's that basically telling us is to find x2, we're going to start with x1 equals 2.1. So x2 is going to be found by putting x1 into this equation, and x3 by putting x2 into this equation, and so on. How does that work? How does that give us basically the answer to the question, the roots of the equation, which is we're going to deal with in part B, in part C actually. Right? How does it actually work to give us a value of the root? Well, I'm going to show you now with this little animation. Okay, so here we have something from GeoGebra, as I just mentioned, GeoGebra, where we're going to try to illustrate what's happening when we are doing this, what's called fixed point iteration, to find the roots of an equation. So what we started off with was this f of x equals 2x cubed plus x minus 20. And we were asked to make x the subject, the x in this place over here, the subject, which we did. We end up with the cube root of 10 minus a half x. Okay. And basically, what we're going to do now, because this is x equals the cube root of 10 minus a half x, or x equals the cube root of 10 minus a half x. Okay. So what we're going to do is we're going to draw the line y equals x, which is this one here. And we're going to draw the curve y equals the cube root of 10 minus a half x. Okay, which is done by GeoGebra for us. And basically what we have to try to do is to find this point where they intersect. And that would be the roots of, the solution to this equation will be the same as the solution to this equation, because this equation and this equation are basically the same thing. We've just rearranged the x here to make it the subject. What's happened there? Sorry, 1 second. Okay, to make it the subject. All right. So if I am able to find, the point where they intersect, all right, which is over here, then I will be able to answer this question. Okay. So now, how does iteration work? Well, this is the question told us to start from x equals 2.1. So we're going to start with 2.1. All right. Now, that's the point over here somewhere. I'm going to zoom in to this section over here so we can see what's happening when we do the iteration. So we're going to replace the x in this equation with 2.1. And what will happen is we're going to see where it hits the curve. Because it hits this curve. And that will give us an output. This I've called it g of x in our question. All right, so just consider that g of x. So what I'm going to do now is I'm going to start the first iteration, the one iteration. So it's going to tell me where 2.1 hits the curve. It's going to give me a value where 2.1 hits the curve. Okay, this point over there. Now, this is the y value, the output of this equation. When I put x equals 2.1 in there first, they always give you a value close to the root. Now, what happens next is, I'm going to zoom in even more. Okay, this value of y equals 2.1, okay, is going to give us a value. If we think about it, that's now going to be the input of the equation. Again, we're going to replace the x with this new value, x1, to find what x2 is, or x1 is. We put x0 here. To find what x2 is, we put x1 in here. So we're going to put x1 into here, okay, which is this value, and then it will give me x2. Okay, and basically what's happening is this value has the same y value as this, and that's going to be the new input. So the new input is going to start from here. Okay, because this is y equals x. This is line y equals x. So whatever value y value this has, okay, that's going to be the new input. So you're going to have this kind of situation where, okay, you'll have a line going from there to there. That will be exactly the same y value, and that's going to be the new input for the equation. So it's going to give us an output up there somewhere. So when I put the next iteration, it's going to give us a value up there somewhere. Okay, as you can see, it's going up here. Okay, it's getting, as we can see, closer to the root. All right, then we follow the same process again. This output value goes back into this equation, and it gives us the next value. Okay, and basically that's going to be, this y value of here is going to be the same as the x value over here, because this is y equals x. So this value of y and this value here of x is the same. Okay, so this x value is going to go into the curve, and we're going to get the third iteration. Okay, and you see it's going to give us something even closer and closer to the root. Okay, if we zoom in, we can see that. Okay, so it's getting closer and closer to the root. Okay, we can go to that's the next iteration here. And if we do this again for the fifth one, it's going to give us something even closer down here. So that gives us this gives us a new input value, and then we're going to put this new input, which is this y value here. This y value here is the same as the x value on this line, because this is y equals x. So the sixth iteration is going to give us something over here. And as you can see, the numbers are starting to settle down, and it's getting closer and closer and closer to the root. We're getting a value that's so close to the root, it's like correct to so many decimal places, close to the root. Okay, so as we get further and further in, the iterations, we can go as many times as you want, and we get closer and closer. The more iterations you do, the more accurate your answer will be. I've kind of lost it now, here somewhere. So the more it's like the more iterations you do, the more you zoom in, and you can see that it's making this kind of spiral kind of shape. This is called a cobweb. Sometimes the root comes by what's called a staircase. When you have something, for example, like maybe something like this, and you have a line like this, and basically you choose an x value over here, it gives you an output over there, and then that becomes a new input, gives you output over there, then that becomes a new input. This is always like y equals x, you see where it's make x the subject, new input. Whoops, what happened there? Lost it now. Okay, so basically it makes a staircase kind of shape. I don't know where's everything gone now. I've zoomed so far in. Okay, there we are. Where's me drawing? It's over here. So small now. Okay, so this type of situation is called a staircase situation. Okay, a staircase. Okay, so it looks like a staircase. It zooms in. Sometimes you have a situation where you spiral to the solution. Sometimes you have a staircase effect. Sometimes what happens is you might have something like this. If you choose a value too far away from the root, too far away from the root, okay, like for example here, or on the wrong side, if you choose this value here, for example, for your initial value, what's going to happen is going to diverge away from the root. It won't get closer and closer to the root. If you chose a value on this side, it will take you closer to the root. That side, it will take you away from the root. So that's sometimes what happens. Okay, so you have to, all the situations that we will deal with in P3, they will take you to the root always. You don't have to worry about any of that divergent, convergent. You don't have to worry about this cobweb or staircase. None of that stuff we have to worry about in the P3 exam. We just have to know how to do the procedure. But this is just a bit of a background to show you how the process of fixed point iteration actually works. Okay, just a little slight introduction to it. So those of you who are wondering, what am I doing here? They'll understand how the thing works. That's all. Okay, so back to the question now. Okay, now, so back to the question itself. All right, so basically, hopefully you understood how the process works now. So we basically made x the subject of the equation. Okay, and we draw y equals x on and y equals this on the same curve, and we see where they intersect, and we use fixed point iteration to home in on the solution. All right, so this is practically what you have to do in the exam. You don't have to understand any of that stuff that I showed you in GeoGebra. If you didn't understand it, there's absolutely no problem. You have to remember this procedure. Okay, so how do we do this? Well, we want to find what x1 is. So I would suggest for x1, you write down the values, and for the others, you don't have to write down the steps. So here, I would say you write down your steps. So you have the cube root of 10 minus a half times, this is going to be x2, sorry. I have x1 already. x2 is going to be 10 minus a half times whatever x1 is, which is 2.1. That will give us x2. All right. So now, how I suggest you set this up is as follows. Take your calculator. You can make your life very easy with the calculator in this question. So we take the initial value that they ask us to choose, this value which is close to the root, which is 2.1. And you just press equals. You press equals, that is now stored in your calculator as the answer. And then you set this up in the way, as I'll show you. So we want the cube root of, we got 10 minus a half. We're going to put, now instead of x, n, I'm going to put answer. A half, and I'll put times answer. Okay, so that's the cube root of 10 minus a half times x. X is answer. So now, because I put 2.1 and press equals, the answer in the calculator at the moment is 2.1. So when I press equals, it's going to give me x2, which is 2.076. It says correct to 3 decimal places. So it says find x2 and x3 correct to 3 decimal places. So I'll first write it down to more than that, which is 2.07622. 2.07622, which to 3 decimal places is 2.076. And then x3 is going to be the cube root. Now I don't really have to write it down, but I'll write it down anyway. But after this, the rest of them, because only 2, I'm going to write them both down. Okay, 10 minus a half times 2.07622. Right, you're going to put the more accurate version in, but you don't have to worry about that because all you've got to do now is press equals. Why? Because now this is the new answer in our calculator. So when you press equals, it was going to put this back into the equation. So when you press equals, it's going to give us a value that's even more accurate. So it's 2.077143, 2.077143. So to 3 decimal places, that's going to be 2.077. Okay, so 2.077. Okay, so those are our answers for part B. Okay, so the more you press equals now, the closer and closer you're going to get to the actual root. Okay, now part C is telling us something else. It's saying use a suitable interval, show that 2.077 is a root of the equation f of x equals 0, correct to 3 decimal places. I'm just going to show you that if we carried on doing this, we'll end up with, this is our root to 3 decimal places. You keep pressing equals, as you can see, all the numbers settle down eventually, and you'll get something which is fixed in this place. So that's the root to however many decimal places. But they want to show that 2.077 is a root of the equation, correct to 3 decimal places. Now, in order to do that, they want us to use a suitable interval. We have to think about the following. Okay, so this is now showing that this is a root, justifying that this is a root to 3 decimal places. And it has something to do with limits of accuracy. So let's say that this is the root 2.077 to correct to 3 decimal places. All right. Now, if it's correct to 3 decimal places, which is like 0.001. Okay, if you divide that by 2, it's going to give you 0.0005. Okay, so basically, if we take away 0.005 from this, it's going to give you 2.0765. Okay, and if you add 0.005 to this, it's going to give you 2.0775. This is called the lower bound, and this is called the upper bound of our solution. Okay, that's the lower bound and that's the upper bound. Okay, so any number, any value of x which lies somewhere between these two points, when you round it to 3 decimal places, it will become 2.077. So anything that's 2.0765 and above, all the way up to just below. That's why it's got the open circle there. 2.0775. So it's 2.0774999, whatever. Anything just below that, when you round it to 3 decimal places, it will give you this as your root. Right? So if the curve, okay, f of x equals 2x cubed plus x minus 20. If 2x cubed plus x minus 20 equals 0. If it cuts the x-axis, if this cuts the x-axis anywhere between these values, it will give you this as a root. So basically, what we're going to do is, just supposing the curve, just supposing the curve goes like this. Just so in this area it goes like this. Okay. Then when I put this value into this equation, when I say f of x is equal to 2x cubed plus x minus 20, if I put f of 2.0765 into here, it's going to give me a value down here. Okay, let's see if it's the other way around. I'll check if it's going to be positive or negative. So I'm going to put 2 times, and I'm going to take the lower bound, 2.0765, okay, cubed, plus 2.0765, okay, and minus 20. That gives us good. It gives us a negative value, right? So that gives us negative 0.01637. Negative 0.016, is it 16? Yeah, 163, 163 ... Just round it, just goes on like this. And when I put f 2.0775, okay, which is the upper bound, into here, let's see what we get. So, all right, I'll just replace this with a 7.5. So that becomes 7.5. That also becomes 7.5. We'll see we get a positive value, which is 0.0105. 0.0105. Okay, so we can justify now that this is the root. Okay, we can justify now that we can say that x equals 2.077 is a root. Okay, and the reason why, let me just go to a bit of an explanation first. The reason why we know that it's a root is that the lower bound, it was negative. The upper bound, it was positive. Somewhere between these two values, it must have crossed through the x-axis where f of x equals 0. Okay, so it must have crossed through the x-axis somewhere between these two values. So wherever that place was, as long as it's between these two values, that value, whatever it is, when you round it to 3SF, is going to give you this. Okay, because it's within, anything within these two bounds will round. When you round them to 3 decimal places, they will round to this value over here. Okay, so as long as there is a change of sign between these two, the upper and lower bound, and it's a continuous function, it's not a function which has like asymptotes or anything like that. This is a continuous function. This is a cubic function here, all right? Then we know that there must be a root that lies somewhere between those two values. So we should make a little statement here. Don't just leave it like this. You can say, as f of x is continuous. So that's a good thing to write down. Is continuous. And, okay, there is a change of sign. There is a change of sign between the lower bound, okay, which is x equals 2.0765, and the upper bound, x equals 2.0775. Okay. There's a change of sign between the lower bound and the upper bound. Okay. So we can say, we can just show that f of 2.0765 is negative and f of 2.0775 is positive. Therefore, a root must lie between them. Okay, that's enough for your answer. Sorry about my bad handwriting. Something like that is fine. Okay, as long as they're going to look for the word continuous and change of sign. Those are the two key words that they'll look for for you to get the marks, right? You don't have to draw this diagram at all here. I'm just trying to explain to you why, okay, if there's a change of sign between these two values, whether it goes from positive to negative or negative to positive, as long as there's a change of sign between these two values in a continuous function, okay, then we know that for sure the root must be somewhere between those values, and therefore, because it's between those two values, if you round it to 3 decimal places, it will give you 2.077. So 2.07077 is a root correct to 3 decimal places. Okay, so there's part C done. Now for part D, it says, hence, state a root to 3 decimal places of the equation 2 times x plus 2 cubed plus x minus 18 equals 0. Now the key word here is hence. Hence, the key word. Why did I cross it out? It's the key word. All right, hence, meaning using your answer to the previous equation. So the previous question, this is what f of x was. Okay. And we know that the solution to 2x cubed plus x minus 20 equals 0 is x equals 2.077, correct to 3 decimal places. So what we need to do is we need to compare these two with each other. We need to compare these to each other, with each other. And it's quite obvious here that there's some similarities between them. You've got 2 times something cubed, you got plus x, and then you got minus a number. Now, what seems to have happened here is that the f of x has now become f of x plus 2. Okay, if you put f of x plus 2, if you take f of x, which is this, and you replace the x with x plus 2, you'll have 2 times x plus 2 cubed, plus, and you'll have x plus 2, x becomes x plus 2, replace the x with x plus 2, and then you got minus 20, which simplifies to exactly the same thing as we've got here, which is 2 times x plus 2 cubed, plus you got x plus 2 minus 20, which is x minus 18. So how does this compare to f of x? Well, we can see that this is basically simply a translation. This is a translation by the vector minus 2, 0. So all the x values, you take away 2 from them. Okay, so the root basically is basically transformed 2 units to the left. Everything is transformed 2 units to the left, including the root. Okay, so therefore, the root is going to be equal to, okay, 2.077 minus 2, which is 0.077. So there is the answer to that question. So it's kind of linked to transformations of functions, right? So it's very important for you to be able to recognize what's happened here. Okay, so there's only a horizontal translation, no vertical translations. So all the x values, you subtract 2 from them when you have something like this. Okay, remember, inside the function, you do the opposite. Okay, so the answer here is going to be the root is 0.077. And if you just wanted to make sure that, it's correct, then when you put this inside here, it should give something kind of close to 0. Okay, so let's see what happens when you put 0.077 into here, just to check if you wanted to, like if you had time at the end of the exam, which most people don't have with the P3 exams. But anyway, if you did have time at the end, you wanted to just make sure you didn't make a silly mistake here, you're going to have, this is going to be plus 0.077 minus 18. It should give you something quite close to 0. It won't be exactly 0. Actually, no. Yeah, it should give you something close to 0. What's going on here? 0.077, 2.077. Yeah. Plus 0.77 minus 18. Give me a second here. 2 times, sorry, what did I forget to do here? Plus 2, sorry about that. Plus 2. Okay, so that's x plus 2. Okay, so press equals again. Yeah, it gives us something really close to 0. If you go back, if you do this, It's like minus 0.002. So it's very close to zero. Okay, of course it's not going to be exact because this is iteration. It gets you won't get the exact root unless you go into lots and lots of decimal places. But this gives you something close to zero. Okay, very close to zero. So you can, if you get something very close to zero, you've done it right. What I forgot to do is I forgot to put the +2 inside here before. I just put x cubed. It was x plus 2 cubed. That's x plus 2 cubed. Okay, so that just shows that we've got the right answer, just to be sure. And that concludes this question. So I hope that was clear, and I hope it gives you a bit of clarification as to how to deal with or how to understand how fixed point iteration actually works. As I said, that part you don't really need to understand it. Okay, it's just something which might enhance some of your understanding. A lot of students ask about it. It's a bit of a mystery for some students. How does it give you the roots? Hopefully you got some idea from that little GeoGebra type of activity. So other questions from this paper, if I answer them, will be in the playlist that will appear in the top right of the screen at the end of this video. Other questions from the topic of numerical methods from P3 you can find in the playlist over here. You can subscribe to my channel by clicking on this link, and the video up here will tell you how to use my channel to find what you're looking for. Thank you for watching, and see you soon.